Good morning, everyone. Thank you for coming to today's Tech Takeover. Today's Tech Takeover is 3D printing design freedom through multi-jet fusion technology. I want to start by giving a brief overview of Automation Alley, who we are, what we do, and then some things to keep on your radar, keep on your calendar from our side. Automation Alley, if you're not aware, is Michigan's Industry 4.0 Knowledge Center. So we think about disruptive technologies and digital transformation and help companies at every step within that process, whether they are just starting out and thinking, oh, 3D printing, I've heard of it, I'm not sure if it's good for me, if it's right for my company, all the way up to industry leaders and innovators like Novastar. So we help companies through a variety of programs. One of them is our Tech Takeover series, which you're all at now. We also do live stream this, so welcome to our live stream viewers. Our Tech Takeovers happen most Wednesday mornings. They're designed to be a very tactile, tactical, implementable technology that companies can put into practice today. And we invite technology providers and industry innovators to come in and present for about 60 minutes, and then open it up to a Q&A at the end. And what these are designed to do is to spark the conversations that will help give your company a competitive advantage by adopting disruptive technologies. Some other things that we have coming up, we've got a golf outing coming up in August. It's a super fun, really relaxed networking opportunity. Everybody within our ecosystem is focused on disruptive technologies and Industry 4.0. So it's a great opportunity to collaborate with other people within that space. And then in November, we've got our Integrate Industry 4.0 conference. Integrate is a full-day deep dive into Industry 4.0, about 50 expo tables, about 30 breakout sessions, keynote presentations, and this year we've got a really innovative roundtable format. So Integrate is November 5th and 6th. Grab your calendars, grab your phones. I know you all have them on you. Mark it on your calendar. I see a couple people, all right. And this year with the roundtable format, we partner with the World Economic Forum on a variety of programming. They see Michigan, as we do, as a very center of applied technologies, right? We all know that we make things exceptionally well. What a lot of people don't know if they're not from Michigan is that we've got a very well fleshed out technology industry and a burgeoning aerospace industry, a defense industry that's super strong. So there's a lot of ways that we look to applied technologies, and the forum has asked us to convene a series of roundtables to get feedback from people who are doing the work today. So at Integrate this year, there are going to be roundtables, and that information is going to be funneled back to the forum in order to help them understand Michigan's place in the future economy and the future global economy. So make sure to be at Integrate on November 5th and 6th. The other thing that we have is our Technology and Industry Report. And our tech report's about 150 pages. We put it on in conjunction with 10 university partners. They each have corporate research underwriters. It is chock full of case studies, action items, and it's designed to be a projection of 3 years down the road, 2-3 years down the road. What do you need to have on your radar and have a plan in place for to keep up to date with the future of manufacturing technology? So if anyone would like a copy, please see myself, see Tony, our account manager in the back. We'll be more than happy to provide you with either a digital copy or, if you like schlepping around paper, the hard copy as well. Some other things that we do during the year, we've got a couple of brand new programs. We've got a My Smart Factory Tour, where we take university and trade school students to smart connected automated factories and have them see what manufacturing of today is. And then we also have our Supplier Reboot, which is designed for Tier 1s, OEMs, and chambers of commerce. They identify companies within their ecosystem that they're concerned about, that aren't necessarily ready for digital transformations that they are going to be sending down their pipeline. We bring everybody here. We bring in technology providers and companies that can speak to these technologies and what they can plan for and how companies can innovate. And it's a full day to upskill the supply chain and upskill manufacturing, keep supply chain strong, and keep manufacturing onshore. So that's a bit of an overview about some of our programming. We do quite a bit here at Automation Alley. I want to hop in a little bit more to 3D printing. So 3D printing is one of those things I hear about quite frequently. It is a game changer, but a lot of companies have no idea where to start. They don't know what it means. and they don't want to be the one to hold up their hand and say, I'm not sure what that means. They don't know if it's applicable for them. They're not sure what products it might be useful for. And that's why having partner companies like Novastar is vitally important to the health of the ecosystem and the health of Michigan supply chains as a whole. I want to digress a little bit and talk about Novastar in particular. I had the opportunity of coming to a networking event we had there, oh gosh, within a month of me starting at Automation Alley. And I met a gentleman there, and shout out if you're watching the live stream, you're going to know who you are. And we got talking about his journey at Novastar. And he started throwing parts, just basic manual labor stuff, but he had an interest. He had an interest and he was excited to learn. And Mary and the team at Novastar gave him an opportunity to grow. And he has grown into an exceptional technology rep and now helps companies implement 3D printing solutions. And if you are watching, they now do color printing. I want dibs on that clownfish. I saw it on your LinkedIn profile. It looks amazing. This is what we talk about with companies all the time. Invest in your people. Your people are your greatest asset. So I challenge all of you to go back to your companies and find someone who is excited to learn something and grow them and develop them and invest in them. And companies like Novastar are a testament to the value of investing in your employees and allowing them room to grow. So with that, we've got two speakers today. We've got Dave Smith, Account Manager at Novastar Solutions. Hello, Dave. And then we also have Paul DeWise, Sales Engineer at Forerunner 3DP, who is back there, and he will be joining us shortly. And with that, I'm going to turn it over to Dave.
Got it. Thank you. Okay. Thanks. That was a nice introduction. Thank you so much. As mentioned, my name is Dave Smith, and I'm an additive manufacturing specialist with Novastar Solutions. We are an HP 3D printer partner of Hewlett-Packard, and we're headquartered in Livonia, Michigan. And we're presenting today. Hopefully you've had a chance to take a look at some of the parts that we brought and that Paul brought, and we'll be here afterwards, so we'll be glad to answer any questions that you have and talk to you about those parts. So let's see, make sure I have this working properly. So as I mentioned, Novastar is a partner of Hewlett-Packard 3D printers here in the Midwest. And even though this is not a product presentation, but I'm going to have some videos and give you some information during the course of the discussion this morning, so you have some context for the information that we're going to be presenting. But I do have a question for those of you here today. How many people here today own a 3D printer? Okay, so not that many. How many people have used or seen, before this morning, used or seen parts from a 3D printer? Okay, so we have a few more. So this technology is a little different perhaps than what you've seen before, which gives the products a lot more functionality, but you'll see that as we present through. So in a way to kind of kick things off, I am going to show a brief video.
Introducing the HP Jet Fusion 3D printing solution, made up of a printer, build unit, and processing station with fast cooling. Now you can deliver functional parts up to 10 times faster at the lowest cost. HP software enables easy job preparation and accurate job monitoring. The HP Jet Fusion 3D processing station with fast cooling is designed for a cleaner, more efficient 3D printing workflow. Replacing materials is easy. With the materials loaded, the HP Jet Fusion 3D build unit slots into the printer so that production can start. Preprint and in-printer checks enable predictable, quality output. HP Multi-Jet Fusion technology delivers extreme dimensional accuracy and optimal mechanical properties faster. Once the print job is complete, the build unit can be moved on for post-processing, and the next unit slotted into the printer so you don't have to stop production. The HP Jet Fusion 3D processing station makes post-processing easy, from faster parts cooling to cleaner unpacking and materials reuse and mixing. Keeping the powder contained so that you don't need an additional room for parts removal. New HP 3D High Reusability PA12 leads the industry in reusability, so there's less waste and less cost. And the HP Multi-Jet Fusion Open Platform gives you access to a wider range of future materials and applications. HP Jet Fusion 3D Printing. Start producing more functional parts within the same day, up to 10 times faster and at the lowest cost. HP, keep reinventing.
Okay, so to kind of dive in and recap a little bit of what was in the video, the fusing or the printing process is really a four-part process. We put down 80 microns, an 80 micron layer of fresh powder. And then we apply two different agents. The one agent that is indicated here with the black is what's called the fusing agent. And the agent that's indicated by the blue dots here is a detail agent. So basically the fusing agent goes down where you want part. The detail agent is immediately adjacent to that where you don't want part. And then that enables you to give you very high resolution. So if you look at some of these parts, and there's a part there, it's like a knurled nut. The detail agent really enables that kind of detail on the part. Once the fusing agent and the detail agent is laid down, we pass over with a heat lamp. And where the fusing agent has been applied, the parts fuse. And where the detail agent has been applied, it inhibits fusing so that it does not fuse. And then once the heat lamp's passed over it, you have that layer that's properly fused or unfused as where you don't want part. And it just does this over and over again in 80 micron layers to build up the part. The nice thing about this technology is that it's fusing multiple layers every pass, so you get really good entanglement between the layers, so you get really good material properties. They're very strong, and the parts are also airtight and watertight as a result of this technology. And here's another video that dives a little bit into a little bit more just of that fusing process.
To produce truly functional parts, it's important to ensure that the material has been properly fused and that part edges are smooth and well-defined. To achieve part quality at speed, HP invented a multi-agent printing process. In this process, a fusing agent is applied on a material layer where the particles are meant to fuse together. A detailing agent is applied to modify fusing and create fine detail and smooth surfaces. The area is exposed to energy, and reactions between the agents and the material cause the material to selectively fuse together to form the part. The fusing process requires accurate temperature control across the entire material layer.
One thing to note is that that fusing process, it's not a chemical process, it's actually a thermal process. So the parts remain recyclable, and that's very important to some people. So Hewlett-Packard has developed the multi-jet fusion technology. Hewlett-Packard also makes a lot of other parts, a lot of other products. So one of the things that HP did when they brought out this new technology, they said, let's go back and take a look at the products that we're already delivering or will be delivering in the not too distant future and see what we can do to use 3D printing, additive manufacturing in the use of these products. Now, there's an adage in, well, all through business, but particularly as it applies to 3D printing is, if it doesn't make dollars, it doesn't make sense. So you don't want to use 3D printing just for the sake of using 3D printing. You want to use it in a situation where it's going to add value. And these are the design considerations that HP looked at. Say, if we're going to redesign a part, what's the criteria that we're going to use? And reducing weight is something that you'll see quite often. Reducing multiple parts into one part. Speed up development cycles. Optimize additive manufacturing. Optimize the manufacturability of the new 3D printed parts. And also to enable some complex geometries that you couldn't achieve any other way. So what we're going to do is we're going to do a deep dive on each one of those criteria. So the first is the design freedom to lightweight parts. This is a picture of a large format Hewlett-Packard printer that's used in commercial applications. And what each one of these printers, it makes these incredibly lifelike images, and they have a spectrophotometer as part of the printer that's actually monitoring the output of the printing process to make sure that it's what it should be. So what they did was they took one of the supports that's used for the spectrophotometer in this printer, and they decided to go ahead and manufacture that with 3D printing technology. So this is what the part looked like originally. It's aluminum. It looks the way it looks because that's the easiest way to machine an aluminum block to achieve the function. So it was designed this way because of the manufacturing material and the manufacturing process. It weighs a little over 12 ounces. What they did initially was they basically just replicated the design, but they did it with a 3D printed part. And you'll see this very often in industry. People will take parts that they've manufactured a traditional way, and they'll basically replicate it. Now, the only support structure you need at the top of this device is that little pillar on the left-hand side. So that's there. So all they really did was took the existing design and removed the material that you don't want. You wouldn't do that with the aluminum block because it costs money to do that machining. It's not in the way, you just leave it there. But it is extra material that you've wasted because it's just there for the purpose. Plus all the material they had to get machined out was wasted. So first iteration, they just did this block pattern. It looks very similar to the initial part. Then they said, okay, we can lightweight that. So if you lightweight it, you can use a smaller motor, which costs less and will typically be more reliable. So they basically just went in and they just lightweighted it some, put some holes in it. And you can do that. Again, you wouldn't do that with a traditionally manufactured part because it costs additional money to remove the material. But if you're 3D printing the part, it's just as easy to print that as that, but you have less material, less weight. And then they went one step further, and they went with something that's called topology optimization. They said, okay, give me the minimum possible material that's still strong enough for the part. And this topology optimization is a trend that's really growing in the industry. And there are several software packages, and you basically input in some design parameters, and it will give you 15 or 500 options of how you can do it. You can't make a product like that with traditional manufacturing methods. You just can't do it. But with additive manufacturing, with 3D printing, the complexity is free. So if you take a look at all of these parts and the progression they went through and what you wind up with, the final part was the weight was reduced by 93%. Weight was reduced. So this final part weighed only 7% of what the original part weighed, and the cost was 1/2. Yes? Okay, so the question is, does it hold the same rigidity as the original part? And the answer is no, but it's sufficiently strong. So the aluminum part was way overkill for what you needed. So when you design these parts, you have to know how strong does it need to be. And that's part of what you put into your design criteria for this topology optimization. So no, the part on the right is not as strong as the part on the left. but it's more than twice as strong as it needs to be for the application. And that's the real question. You know, the part on the left is way overkill, but it's pretty easy to machine a block of aluminum, but it's expensive, it takes time, and it does add weight. Even though it's aluminum, it adds weight, which means you need a stronger motor now than you would otherwise. The next design criteria we're going to look at is replacing many parts with one. So the part on the left is the original part that Hewlett-Packard uses. This part is actually used in the manufacture of the Hewlett-Packard print heads, which are very high resolution. It's 1,200 dots per inch, very precise location of the holes, and they basically laser drill the holes. So they had this part on the left was a tool that's used to basically run water through and flush out the sludge and keep the part cool while it's being machined. The part on the left, as you see, it's 7 subparts, and they're either machined or stamped or extruded. They replaced that design with a single part that was injection molded. And I don't know if you can read this, but in terms of reduction, it went from 575 grams down to 52 grams. The cost went from $450 to $18. And the manufacturing time was reduced from 3 to 5 days to 1 to 2 days. So the part on the left, you can see that's the final part that's all assembled. The middle part, all the component pieces. So reduced the complexity in a very significant way. It made it much less expensive. You'll not know that by the price of buying an HP printhead, but it did have a substantial impact. Yes, question? Yeah. Yes. Well, the left-hand side is being produced with traditional machining methods, CNC and extrusion, and then it has to be assembled together. The printer on the right, one of the things about the multi-jet fusion technology is it's printing in a powder bed that's 11 inches by 15 inches by 15 inches tall. So you can be producing many of those in the same print build. And it's typically an inch an hour, and you can have, in the 15 by 11 XY footprint of the printer, you can be printing multiple of those with every pass, and you can have multiple layers. So I don't know how many of those you could print in one build, but you could print quite a few. And again, the left process, it's all CNC and extrusion, you know, so there's certainly a lot of time involved with making those too. So when you talk about some products, it's hard to scale up CNC machining, and because you just need more machinery and more operators. So if you're comparing it to injection molding, that's one thing. But if you're comparing it to traditional machining methods, then again, it's going to take some time. Did that answer your question? Okay, thank you. Here's another example of a part where they combine many parts into one. And this is actually a part that's used in one of the newer HP 3D printers. The injection molded version required many parts, and the multi-jet fusion was actually, they could do it in one part, but as we'll talk in a minute, they actually did it in 2 parts just because it was easier to manufacture that way. So they were able to reduce the cost by over 30% and eliminate a lot of capital expense also. And not only that, but the multi-jet fusion 3D printed part had better functionality because you were reduced. You were able to eliminate some of the design constraints if you were going to injection mold this part. So the airflow characteristics and the performance of the part was better than the injection molded part, and that was enabled by the 3D printing technology. Another thing that Hewlett-Packard, another criteria they used as they looked at parts to use 3D printing for was that we want to get these products out to market more quickly. This is a little Hewlett-Packard 3D scanner that you can use to scan parts. And what they use 3D printing to take some of the, internal components and 3D print those rather than injection mold them. One of the advantages of using this technology is it's real easy to go through and say, I want to test 5, 6, 7, a dozen different iterations of the same design to see which one works better. And you can print them all in the same build, run them all, and then test them out, see how they work. Injection molded parts do a great job of creating parts, but you have to design the injection mold. You have to machine it. They're typically fairly expensive. If you make a slight tweak to the product, you have to go through and create a whole new mold. With 3D printing, it's really not a problem. And again, you can do multiple iterations at the same time and print them in the same build. Let's see. I think we actually have a video on this as well.
This is the HP Z3D camera, and this is the first product from HP's computer business, Personal Systems Group, that used multi-jet fusion in development and in production.
When we see HP start to use some of their own technology in their own products, I think that's one of the neatest things about working with HP is their willingness to look at the technology and instantly bring it into their product development and then right into their products. The biggest advantage of multi-jet fusion is its speed and the quality of the parts.
We had the luxury of being able to iterate the design rapidly and do more testing. And we did that thanks to our partners, Protolabs, who were able to be very responsive, give us very good quality parts, and produce nicely dyed black parts.
Being able to work with HP using their own product is really neat, and finding new applications within different divisions of HP to really test the limits of product development and looking at new ways of bringing products to market quicker.
I have been developing product for HP for a long time, and I never had the chance to have 3D printed parts I could take to production.
The disruption that HP has created with the multi-jet fusion has allowed for customers to really rethink how they design their parts, both for prototyping and production, and has opened the door to changing really the future of what manufacturing looks like.
Comment made in the presentation was a company called Protolabs. And Protolabs is a digital manufacturer, as is DeWise, Paul DeWise and Forerunner 3D. So Hewlett-Packard has partnered with a lot of companies throughout the country and basically to provide manufacturing capacity to people who want to take advantage of this technology. So rather than printing parts ourselves, we partner with local businesses that develop the expertise, have the equipment, and can actually provide these parts to customers who can't justify the cost of their own printer. One of the other criteria that Hewlett-Packard looked at was how can we use 3D printing to optimize the manufacturability of some of the components that are used in our equipment. And this is the part you saw earlier that was designed for additive manufacturing. So we can now print it, 3D print the part. It's less expensive and has better performance than the injection molded part. But because of the geometry of the part, we could only build 3 at a time in the build unit. So they tweaked the design slightly and broke it into 2 parts that could easily be assembled. And they can now fit 8 of these print parts in one build. So more than doubled their throughput just by a slight redesign of the part. Here's another example. If you take a look at that bracket, I'm not quite sure what it is, up on the left, and we could print some number of those in the same build unit. But if we take it and we actually open it up and print it in the open fashion, we can now print many more. And what's interesting is that the part with all the folding pieces was all printed as one part. So there's moving parts in there that it was printed that way. So all they have to do is take it and snap it together when it comes out of the build unit, and it works. It enables them to really maximize the capacity. And for people like Paul that print parts for customers, he'll tell you if more parts he can get into a build, the less he has to charge you for making those parts. So the fact that we have this kind of flexibility using this technology has a lot of pluses, including the fact that now parts can be made in a more cost-effective way. One of the other criteria that Hewlett-Packard looked at is, are there parts that we can combine and things that we can do with complex geometries that we couldn't do before? This is an example from a consortium in Europe, and it's IM3D Hub. It's similar to the America Makes consortium here in the United States, if you're familiar with that. And it's a private-public consortium, and their objective is to help companies be more competitive. And so they developed this part, and I've got a video that shows how it works, that can be used for picking. It's a robotic, and it's a pneumatic application. So that was all printed as one part. And it would be, I can't think of a way to print or to manufacture a part like this other than using 3D printing. The parts can be very fragile. This one's been tested for 1 million cycles. And because of the parts are fully fused as they're being printed, you can use them for pneumatic and hydraulic applications, which is not true of most 3D printing technologies. We've talked about a lot of the parts that Hewlett-Packard's done internally using 3D printing. This is a part actually from another one of our customers, a company called EMI. They're down in the Cleveland area, and they make some end-of-arm tools for robots. They also make conveyor systems. And the product on the left is their original design, and it's basically a robot grabbing device. And it's used with a collaborative robot. And one of the things about collaborative robots is they're collaborating with people. So they tend to be fairly low power because they don't want to inadvertently destroy somebody or kill somebody. So the payload is fairly limited. The original tool, even though it was made of aluminum, was 1,426 grams, which is almost 3 pounds, I believe. Then they replaced that with a design on the right, and it was 3D printed. And they reduced it by a factor of 2/3. So it's only 1/3 the original weight. It's really important because anything you can do to lessen the weight of the tool goes directly to payload of what the robot can do. The mass is a lot less. The component count has been simplified, went from 17 down to 11. The assembly time was more than cut in half, and the cost is 23% less. Again, that's not a huge cost reduction. That's kind of the icing on the cake because of all the other things that they gained. No, it's strictly the manufacturing cost. Yes. Now, one of the things that's really intriguing about the Hewlett-Packard technology, it's now the 3D printers print parts for the HP 3D printers. And if you take a look on the right, you'll see some parts that you might have seen in other parts of the presentation. So the HP Series 500 3D printer has over 140 parts in the printer that were printed by HP multi-jet fusion printers. So they are using this technology heavily. And 3D printing with multi-jet fusion, at least, is no longer just a prototyping tool. It's certainly something you can use for full production parts. If anybody has any more questions, I will be here afterwards. My contact information is up on the screen. We are having an open house at our demo center, which is in Livonia, Michigan, on July 25th. We have some cards in the back with that information. We invite you to come out and take a look. Again, it's an open house. It starts at 10, it ends at 2. Come when you want, leave when you want. We'll have food and beverage. You'll get to meet our application engineers, you get to see other parts, talk about applications. So we encourage you to stop by. Now, at this point, I'd like to introduce you to Paul DeWise from Forerunner 3D. And Paul is a customer of Novastar's, and he has a service bureau and production company. He also does design work. If you could just stay in there for a minute. So when I first met Paul, and by the way, Paul is doing some really cool things, which you'll see. And if you're on LinkedIn, I encourage you to connect with Paul, because he really posts some really cool stuff. But so I'm really excited to see what he has to say today. But again, follow him on LinkedIn. It's some good stuff. So when I first met Paul, I think it was in January. We were at an event downtown. And when I came home from talking with Paul that night, my neck was really sore. And I'll tell you why. Paul, if you could step up on the stage here. So I'm like doing this the whole time we're talking, and it just killed me. But it was still a good conversation. Anyways, I'll turn it over. I think you have to turn that microphone on. I think she turned it off when she was done.
Test, test, test. Oh, there we go. All right. Well, hello, everybody. Let me change out my presentation here a second. All right. Oh boy, here we go. Oh, there we go. All right. I was like, now the slides aren't even working, let alone the videos. All righty. So, so my name is Paul DeWise. I'm the sales engineer and owner of Forerunner 3D Printing. And let's see here. What time do I got to have this wrapped up? Because I'm kind of verbose. Okay, perfect. So we'll get right into it. So my background in 2010, I started a CAD design engineering firm, DeWise Engineering. Actually wearing the wrong shirt today, so I got my DE shirt on. So we started out in the engineering world, and about half of our business was machine design, automated equipment design, shop floor hand tools, shop floor equipment, things of that nature. And so, from 2009 to 2016, built that business up with a couple of employees. And in 2016, I had an opportunity to purchase the assets of an existing 3D printing company over in Muskegon, Michigan. We're actually located on the west side of the state. We're over near Grand Rapids, a little town of Coopersville. So purchased the assets of this 3D printing company. They'd been around since '94. They were one of the very, very early ones to the industry, and got two SLA systems with that purchase. And so went along for a couple of years, kind of having my engineering business and this 3D printing business, and kept running into this situation where my machine designers would be sitting there and they're looking at a part that they've got a nest or a gripper that they need to design. And the conversation would always end up with, man, wouldn't it be cool if we could just print this? Because think of what we could do. And it was always like, yeah, but we can't because the materials suck. And that was the big thing that held us back. Materials in 3D printing have sucked for a long time. Finally it got to the point where we said, you know what? We got to find a solution, because there's this huge opportunity for automated companies and machine builders and integrators to use additive. We just need to find an additive technology that we don't have to shoehorn their application into the additive technology. We need to find an additive technology that naturally fits in with their business. And so, went out and we looked at everything. I mean, we looked at 3D Systems, we looked at Stratasys, we looked at EOS, we looked at Carbon, we looked at HP. And by the time it was all said and done, HP was the clear winner for us as supporting machine builders. And that's really where we started, is with very focused on machine builders. But then once we got the HP machine, we started to realize, holy smokes, there's all these other incredible opportunities around this technology. Like Dave's talking about with production. And we have actually fallen into doing a lot of production. This presentation is very much for automation and machine build companies. Dave's already done a great job of kind of talking through production, so I'm not going to go too deeply into that. I'm going to focus more on kind of like the job shop type environment, onesie, twosies, 3Z, 4Zs, maybe 100 of something if you've got a machine that's got a lot of duplicate components on it. So we're going to jump into things. Feel free to raise your hand, ask questions. I've got a lot of content I'm going to try and cover here, so feel free to stop me. Okay, so one of the things about being in the machine build world is machine designers are some of the most skeptical people in the world. You come in and you go, hey, I've got this really cool new technology. Look, we can 3D print all this neat stuff. It's going to change the way we do things. You're going to be able to do all this neat stuff. And they go, that's great. How strong is it? And I'm like, well, it's super strong. HP gave me this piece of paper. It says right here on the material specs, it's super strong. And they're like, that doesn't mean anything to me. What does super strong mean? I'm like, I don't know, man. They're like, well, you got to prove it to me. So we went back to the office and we played around and we said, hey, let's build a pull tester. Let's get a scale off Amazon and a hand crank off an old boat trailer, and let's start breaking this stuff. So this is actually a video that we did. This is a test coupon right there. And we actually not only 3D printed the eye bolts to either side, we actually 3D printed the threads onto the eye bolts and into that test coupon. Now this is a 3/8 16 thread with eye bolts on either side, and we just start cranking on it. And you can see we're up to around 345 pounds before that part breaks in tension, okay? And this is the same material you see back there, those gray parts, the black parts are the same. It's PA12. It hasn't been treated with anything. There's no inserts. It's literally just 3D printing that you're seeing there. Now this is a half 13. We got this one all the way up to 650 pounds, and we started to actually break our pull tester. So we stopped in this video because I didn't want to get hit in the face with a metal clevis. But eventually, we rebuilt the pull tester, and we got up to 900 pounds before we broke these half-inch fasteners in MJF. So this material, like I said, from a strength perspective, is just insane. And by the way, that's pulling on 3D printed threads. I do not recommend you 3D print your threads. Use key inserts, use helicoils, use inserts, but this is a testament to what the material is capable of. So let's see here. And this is actually, I'm pulling it apart, and it'll show you here in a second. It didn't actually permanently deform the threads or anything. The threads screwed out just fine. It wasn't like it plastically deformed them inside the part. So that's a pretty good indicator of, again, part strength. So yeah, there we go. So let's see, here we go. So the next thing was, I go back to my machine builder. I go, see, here's a video right on my phone. It's super strong. He goes, great. How wear resistant is it? How wear resistant is it? And I'm like, it's super wear resistant. He's like, qualify that. I'm like, back to the lab. So we go back to the lab, and as machine designers, we designed a little wear testing machine, and that's what you're seeing a video of right here. So we built this 80/20 frame, aluminum jig plate with a bunch of dowel holes and bolt holes drilled into it. This detail that we're testing, this MJF detail, is actually sitting back at the back of the room there. So feel free to check it out at the end. We put it in, we lined everything up on this 80/20 frame, tightened it all down, and then we loosened the bolts on the cylinder, and we put 10 thou misalignment shims behind the cylinder to actually move the cylinder out of position. So it created about a 7.5 thou interference with that nest. And then we hit it 100,000 times. And over that 100,000 cycles, it actually forced the detail to twist. We didn't actually dowel the detail in place, so that was a mistake on our part, but it forced the detail to twist a little bit. So that's why you're seeing corner to corner wear. Whoops. But the worst of the wear was only about 13 thousandths. So this is a laser scan inspection report that we did of this detail after the 100,000 cycles. And you can kind of see for yourself, you've got the really dark blue ditch on the left-hand view, kind of up towards the upper right-hand side of the part. That's 13 thousandths. Other than that, everything's kind of in that 5 to 6 thousandths range of wear. So we always kind of figure when we're designing machines, worst case scenario, unless something's assembled wrong, it's when a human is putting a part into and out of a nest, because humans are sloppy. Robots are precise, but humans are always sloppy. So we did this to qualify an operator just kind of throwing a part into a nest and you getting those kind of bad wear conditions as the part's getting loaded in and out. And so it held up over 100,000 cycles. Another thing that was really interesting that we want to check, the underside of this part is actually hollowed out. If we call it a material saver. We want to cut as much excess material out of the part as we can, because whatever powder I don't sinter, you don't pay for. So we're trying to cut costs that way. So that 32 millimeter bore running at 80 psi shop air, that's have 100 pounds of force coming down and hitting full power into the bottom of this nest. Over that 100,000 cycles, we lost 2.5 thousandths to compaction. Okay, so even when you're running a cylinder into this stuff over and over and over again, it doesn't deform, it doesn't crack, it doesn't chip, it doesn't even really compact. So this is the type of stuff that really positions MJF to be excellent for end-use parts, whether it's on automated equipment or if, like in Dave's case, you're running production. These aren't the SLAs from the 90s where you carefully set it on the conference room table and then be like, no one touch it, because if we do, it's just going to shatter. This is a completely different animal. So naturally, I continue to go back to my machine builders, and they continue to come up with reasons why they don't want to use this. The next thing was, well, how accurate is it? Okay, accuracy. What can we expect? And so we went back and we printed up some gripper fingers. These gripper fingers are actually sitting back on the table, so you can actually see the parts we actually scanned. Scanned them on the Faro and got this inspection report to come out. We set our tolerance on this to plus or minus 5 thousandths, and we're 97.6% in tolerance. The areas that are falling out of tolerance are not necessarily critical areas. You can see our gripper teeth are all within spec. It's like areas like the top and sides. You're just getting a little bit of shrink on the part. Depending on how you orient the part in the build chamber, you are going to get shrink and warp in certain areas, but we can process around that. So, being that, we know what the machine how the machine will perform when customers send us parts, it's not just like take the part, throw it into the build, quote it, send out a quote. It's more of an interactive process for us. What are you doing with this? What are you trying to accomplish with this? Where do you need it to be really good on tolerance? Where do you maybe not care as much? Because we can process around tolerance issues. But all told, plus or minus 5 is not all that bad. Generally, there's a lot of machine shops that will pretty much run on this level of precision. We've also done a lot of experimenting around with like dowel holes and stuff like that. Generally, if we get up into really large components, maybe something that's 12 to 14 inches in length and is kind of not necessarily dense, maybe it's got a bunch of ribs coming off of it with dowel holes out here. Those tend to warp a little bit more. You're out into more like the 15 to 25 thou plus or minus range. So then in that case, what we've done is we've actually treated these parts almost like a casting. And we'll put them into a bridge port, and we'll actually indicate in and put in the critical dowel features. So you get all of your geometry that you don't really, it's just connecting this area to this area. You don't really care how accurate it is between those 2 points. Machine the dowels here, maybe do a cleanup operation over there, and you almost treat it like a casting. But generally speaking, it's rare that we have to do that. I mean, you have to be talking about a extreme precision operation, like maybe clip driving onto a really temperamental clip feature on plastic parts or something like that. Generally speaking, the accuracy is good enough to do pretty much everything we need in a machine build application. Excellent. If you were to go to like Elro Plastics, buy a block of their PA12 nylon, have me print you a block of our nylon, it's going to machine the same. It's just like billet. It machines very nicely. So the material's good up to, on the box, it says good up to about 360 degrees Fahrenheit. And it's stable up to those temperatures. We've experimented with going over that momentarily. So what we'll do sometimes is have to grab really hot parts out of injection molds, maybe 400 plus degrees. And we'll reach in, grab the part, quickly drop it someplace else, and hit the MJF part with an air blast to help dump heat out of it. And so you kind of get away a little higher temperatures for momentary, but you got to get that heat back out of the part. So you can't necessarily go this fast. You'd have to grab it, set it, and then do an air blast to cool it. Grab it, set it, air blast to cool it. So, but up to that 350 degrees, there's no warp, there's no twist. It's stable. It's stable, and you get good deflection performance out of it. I didn't put any outside for the polar vortex this year. I probably should have. That would have been the way to test it. That's a great question. I do not have a good answer for you on that. We have not had an extreme cold application yet. If you have something in mind, come see me after this, and I'd love to hear what you're thinking, and maybe I can get you some spec parts, because I'd love to know. I don't know, but it sounds like I've got some more testing to do.
A key thing to know is that the performance of the material is going to be basically the same as if the part had been injection molded. So it's, the material properties of nylon 12 are pretty well documented. And then the question is, okay, how bad does the manufacturing technique or technology mess with that? And the good news is that the material properties are very strong. If the part had been FDM, which is filament printers, probably have an issue with layers. If you had sintered the part rather than fully fused it, it might not perform as well. But again, if that material works well in an injection molded application, it should work fine if it's been manufactured using multi-jet fusion.
Another fun heat type application that we tested, we have a company in our hometown that repairs a lot of small engines and stuff like that, and there's this one particular Briggs & Stratton engine where they have an aluminum cast 90-degree elbow that comes off the side of a single cylinder Briggs, and then you've got your carburetor, and it bolts directly to that aluminum casting. And it's notorious where these will be on generators or power washers. The thing will tip over, and the carb will hit the concrete, and it'll break that casting. And that is like a big part of this guy's business is just finding old motors, pulling these off, and selling them on eBay for these castings for like $100 a piece because it's so notorious. So he came to us and said, hey, I would love to try and actually replicate this part in MJF and see what happens. And we're like, it seems like the heat might be too high. I don't know. Let's try it. So we laser scanned, reverse engineered, and printed this casting, and we bolted it onto the side of this Briggs, and we bolted the carburetor onto it, and the carburetor is completely supported by this casting. And then he literally hooked it up to like a 50-gallon gas tank and ran the engine for like a week straight. I mean, literally 24 hours a day. And we ran it outside because we're like, I don't know, it might start on fire. Who knows? It was insane. We went out there after 5 days of continuous operation, and you could still reach down and grab the MJF part because it's so efficient at dumping heat. Whereas, they told me if that was the aluminum part and you grabbed it, you'd be going to the hospital because you're going to need skin grafts on your fingers because it'll be way too hot to touch. So we've just been very impressed with the thermal efficiency that MJF material has to actually dump heat and to get the heat out of the part. So that's one of the reasons why you can go into those higher temperature applications. So. Mm-hmm. You don't use MJF. So I don't want to step on my lovely host's toes here, but here's the honest truth. From me as a guy who runs the machines, if you need something that is injection mold level smoothness, there are polishing. You can tumble the parts. There are some chemical processes coming down the pike that can do like almost like a vapor type smoothing. But even then, it will not be perfectly smooth. You will still have a subtle layering effect to the surface finish. So if you need it to be 100% smooth and perfect, you literally have to hit it with high fill primer and sand it and bench it until you have the level of smoothness that you need. And for us, that's just not, we can't be cost effective doing that. So my honest answer to you is, if you need something that is insanely smooth, MJF is probably not the solution for you. No, I mean, once it is built and sintered, what you feel is what you get. There's no variance in that. We haven't seen any. I mean, we've been running our machine literally around the clock since September of last year, and so we have powder that's seen hundreds and hundreds of builds at this point. That's still being run every day, and we haven't seen any variance in material properties, or surface finish or anything like that. The only thing that varies is color. You'll notice that some of the grays are darker, some of the grays are lighter. The color variation in the gray is the only thing we've seen over running this material for a long period of time.
So for different finishes, or?
So there's nylon 11, there's nylon 12, there's nylon 12 glass bead, there's a TPE material that'll be out later this year, there's a polypropylene that's coming out, we'll say a year to 2 years from now, and then there's a whole long roadmap. The Rapid show was at the Cobo Center here a month or two back, and I went and sat in at an HP kind of breakfast meeting with a lot of machine owners and operators from all across the country, and some of the top people from HP were there, and they are putting a lot of focus on material development. They have this roadmap, and that's one of the things that they've been kind of getting their butt kicked on by guys like me, is saying, hey, where's this flame retardant material that you've been promising, and where are these elastomers that you've been promising, and where's some of the other types of plastic. And so HP has kind of redoubled their efforts, and they're also the really cool thing about this machine, and what attracted me to HP is, in the past, Stratus, 3D, those type of companies, it worked off of the old kind of Gillette razor model. Hey, you buy our machine and you're going to buy our materials. Unlike Gillette razor, they don't just give the machine away to get you to buy materials. They charge you an arm and a leg for the machine, and then they really charge you for the materials. HP is taking a different tack. Their whole thing is BASF, Dow, Polybulk, whoever wants to develop plastics for our process, we would love to have you. We'll even help you qualify your materials. And it's an open platform. So they're allowing companies that have, decades, if not 100+ years of material science capabilities around plastics to come in and develop for their platform. Whereas 3D and Stratus, it's like, no, this all locked up in patents, and we defend it tooth and nail to make sure that we don't lose on material sales. So that's one of the cool things about HP, is there's this huge ecosystem outside of HP that's developing materials. So just because today a material doesn't exist for the system, it does not mean it's not coming down the road. It doesn't mean it has to come from HP either. It could come from all kinds of different companies all over the world.
I want to just add on to what Paul just said. So in the back of the room, we have a couple of sample pieces made with a TPU, which is a thermoplastic polyurethane, from Lubrizol. So you can check those out, and that'll be coming out in the next few months. And one of the nice things about TPUs is that they're spongier, and through use of latticing, you can really impact how cushy or how stiff the parts are. So we, in the fact, the sample part we had, at one end it's very stiff, and the other end it's very soft, and it's all controlled through the lattice structure. The other thing I wanted to address was the question about surface finish, and Paul's absolutely right. If surface finish is the number one thing you're looking at, multi-jet fusion is not going to be the optimum solution. However, there are solutions where it does make sense to do some extra machining. So, for instance, we've printed some light housings for one of the local car suppliers. And the surface finish, as you see from the parts, are fairly rough. But there are companies that have vapor deposition technologies, so you can put down so you have like a mirror finish in the back of the light housing that's a reflector. So that would be cost prohibitive for a production part. But when you're going through design iterations up front, and you want to have a part that looks and operates the way the production part wants to look like, you can use the technology to get those parts very cost effectively, certainly much less expensive than if you're trying to create an injection mold for some prototypes, and then spend a little bit extra time, and the resources are out there so you can do some beautiful fine finishing, and you can metal plate these, and there's a lot of different technologies out there. Again, from a production perspective, if it's high volume, you do want to look at something else. But if you want a prototype part that looks and operates just like the production part, you can certainly get there using multi-jet fusion technology parts.
Yeah, I actually have some metal plated parts in back. They're not polished up, they're literally just straight MJF metal plated, so they won't have the level of polish that he's talking about, but you can at least see what they look like. So yeah, that kind of answer your questions? Okay, no problem. All right, so we'll just kind of skip into things because I kind of already talked about this. So let's look at some examples. And a lot of this stuff is sitting back at the back table, so you can check it out. So we had a machine builder come to us, and specifically we were talking about these details right here. The challenge: take 40 left-hand and 40 right-hand small nesting details that are needed for snapping two plastic parts together. It's actually snapping chrome inlays into a grill. The details are needed quickly, less than 1 week lead time, and some of the details need to be able to press in on Class A plastic surfaces without marring them. So Class A would be a chromed surface, a painted surface, or an injection molded surface that you can't scratch. It needs to have a Class A level of finish for the exterior of the vehicle. So we can fit these 40 or 80 parts of this size right here. We can fit all 80 of those details into a single build, and our lead time to actually produce those parts would be 3 to 4 days. That's from us starting the build to us either delivering them, dropping them off, or the customer picking them up. One of the cool things about MJF is the more parts I can throw in that build, the cheaper your per part cost becomes, because like you saw earlier, we can nest in the X and Y, we can also nest in the Z. And there's no, you think about with nests like this, each one of these nests, each of these 80 parts is different. It's either a mirror image of one of the other, or it's completely different. And so typically in a machining situation, it would be, okay, well, it's going to be 2 setups because I got to put the holes in the bottom, and then I have to do the profiling work on the top. And then I'm going to have to CAM program at least 40 of the details. Then I'm going to have to either mirror my CAM program over to get the other half of the parts, or I'm going to have to completely program those on my own, depending on what your CAM strategy is. Then I got to set up vices in my Haas. Then I got to put, bump stop. I got to indicate all the vices in. I got to, load my programs. By the time you do all that, it's a lot of work. It's a lot of time and a lot of work. Here, you send me the details. I throw them in the build, orient them, and hit go. I mean, it could be, if you sent me the parts at 9 o'clock in the morning for that build, I could be producing parts. I could have that machine up and running by 11, producing parts. And by the next morning, your parts would be done and into the cooling system to start the post-process. There's no programming time. There's no setup time. So then the other thing is, for Class A safe, now MJF parts straight out the machine, it's just nylon. It's not going to be safe for chrome or paint. But what you can do is, there's actually a company over here in the Detroit metro area, Rapid Coating Solutions, I believe is the name. And they have a spray-on urethane type, elastomer type material, and you can spray it on details, and it's impressive. I believe this blue nesting block that you see back there, You spray it on. It's hand applied, so your tolerances sort of go out the window in some regards, because their thickness is going to vary from 30 thousandths to 60 thousandths depending on how it sprays on. But in snapping applications like this, we're just pressing down on the part's already located in position, so we're not really worried about having to have a super critical alignment or anything like that. So if you have a Class A safe application that also needs extreme alignment or extreme accuracy, this process can sort of fall apart for that. But for general applications where it's just nesting details, you just need to set your part on top of it and you just can't mar the part. This is a really good way to do that. So let's see. Oh, that's just a part that I had laying around. It's the metal. The horse is not MJF. The horse is injection molded. So yeah, don't look at that. That's not MJF. MJF? Yeah, absolutely. Kind of like what Dave was talking about. I have little transfer fingers. So we have a customer that does deep draw stamping. So they're running their presses at upwards of 200 strokes per minute, just banging out little fuel injector parts and stuff like that. And they have all these transfer fingers that transfer the stamping through the press to hit all the stations. And what we've been doing with them is they need to prototype all these transfer fingers, and they're pretty complex. So they would spend a lot of time machining these fingers, and then two things would happen. They either wouldn't get the work, so they just ate all that cost, or the fingers wouldn't quite be right, and maybe they could remachine them, but a lot of times they just have to start completely over. So what we did is we started 3D printing these parts for them on MJF, but the trick is the gripper fingers, when they come into contact with the part, they actually close an electrical circuit to tell the press, yes, I have the part, and it's moved to the next station, and now I just dropped the part off. Well, our parts are not conductive, but a machine part would be. So what we did is we actually plated the gripper fingers that we printed so that now they're conductive, so they can use them in their press for doing these prototype studies. And actually, they left one in just to see what would happen. I think we're over 1 million cycles on that transfer finger now, and it hasn't broken yet. Which is 1 million cycles for them is like a week. So it sounds a lot more impressive than it really is. I'll be excited when they get up to 10 or 20 million cycles on it. But yeah, so you can plate the parts, and Dave's obviously seen it where they can plate it with a chrome and actually get reflectivity. Our thing is we're plating it more for either robustness or for electrical conductivity. All right, so I'm gonna kind of skip over a bunch of stuff here because what time do I got to be done? 5 minutes. Oh my gosh, 10 minutes. I'm so far behind. Let's talk price. That's what we're all here at the end of the day, right? Like, what's this actually going to cost me, Paul? Is this $1 million for all 40 of these details? No, it's not $1 million. $17 each. $17 a piece for each of this type of detail right here. And then for the larger, oh boy, didn't want to do that. For the larger details, and actually these two right here I do have sitting back there in gray, so you can actually see them to get a sense of size. The customer actually wanted, I think, 340 of the 340 of the black ones. Those are about $40 a piece. And that would have taken us, all the little guys we could put into one build, the big guys we have to do like 3 or 4 builds. All right.
So Paul, how would that compare with what you would have charged prior to using Jet Fusion?
Half, less maybe, and lead time. That's the big thing. I mean, to get 80 of those little details done with our machining suppliers and kind of where they're at lead time wise, we're probably 2 to 3 weeks if we're lucky. And here it's 3 to 4 days. So that's where our customers really like it, is quick turnaround. A lot of times we get called, when their in-house guys have cut a bunch of details and maybe they made a mistake or it didn't work, and now they're up against a runoff, and then we get the call and they go, all right, well, we did it ourselves and it didn't work. Now we need them in like 4 days. So can you turn them around? And that's not a problem.
Does the price go up then?
No. No. Our standard lead time is 3 to 4 days. Like right now we're running production, so I think we're out. If you place an order today, I'm out to Monday of next week before I have capacity. Then that's where the price comes in. If you go, well, I need to break into your production, okay, then we got to talk about it. But our standard lead time, if I'm running, or if we're not backed up with production, it's 3 to 4 days, and no price jump to get it. What was that? All of them, any of them. Like I said, that's the beauty of us, is we're not only an additive manufacturer, we're also machine designers. So I have CATIA, SolidWorks, Inventor, and Fusion in-house, and we can also take in Pro Engineer, NX. Probably, if you send me an old SDRC ideas file, I'll probably have to have you convert that one for me. But barring that, I can take pretty much anything. Nope, I prefer if you send me a step file, because our machine works off of STLs, and we have our computer set up to export really high quality STLs, and most like SolidWorks out of the box produces extremely crummy STLs, and that's just the settings they have set from the factory, and you don't know what you don't know. So a lot of people will export it, and I always email them back and say, just send me a step file, let me handle the export for you, because then I can get you the best quality part with the lightest weight file size for me. So yeah, step or Parasolid would be my preferred formats if you're sending it out. But we can take SolidWorks or anything else natively if you don't want to mess around with it. Okay, so end of arm tooling. This is a video that HP did. Besides nesting, end of arm tooling is another big one for us. So what's really cool about this is you can run your airlines integral to your actual structure of the part. So HP and a lot of companies, they have these really cool looking parts. They're very organic, and they almost look like modern art. And I love the way they look, but I'm from Practicalville, Practicalville, Michigan over here. So we like square, we like blocky, we like stuff that looks like parts that machine designers make all the time. Now, these parts again are sitting in the back, and one of the things that there's a couple main things on this. One of them is texture. We can print knurling. We can print sharp gripper texture. Like you can see in these renders here, there's actually texture inside the gripper fingers, or inside the fingers themselves. The picture up at the top actually shows, and it's hard to see in that picture, but I have those gripper fingers sitting back there. There's actually a knurling that we print into the part. It doesn't cost you any extra. You think about what it would cost if I had to, machine those patterns in there. I'm either in there with a ultra small end mill trying to chew those things out, or more likely, I'm sitting on a sinker EDM with a graphite electrode burning those patterns in there, and your price and lead time are just skyrocketing. So for us, we just say, we'll print the texture you want, and it doesn't cost you anything extra, because if you take one thing away from this today, this is what I want you to remember. Get out your pens, because this is the most important thing. Complexity is free, size drives cost. So if you have a really small part that is insanely complex, that is like the perfect MJF component, okay? Now, if you have a really big block with almost no complexity to it, that is a terrible MJF component. Go do it on a Bridgeport, go do it on a CNC machine. That's where you want to do that stuff. But even if, and I have some parts back in the office, we've even done really big parts. We do these drums, and they've got a spiral groove cut all the way around the outside of them, and they're actually for singulating stacks of flower pots. So the flower pots are all stacked up, these drums come to either side and start spinning, and they pick the flower pots up one at a time in these spiral grooves, shoot them through a machine to slap labels on the outside of the flower pot, and then it restacks them at the other side. To make this part, you would need to either put it on, essentially need to put it onto a Haas with a 4th axis rotary on one side of it, or you'd have to put it onto a mill turn type machine. And I mean, the part is this big around, and it's this long, and it's a perfect MJF part, because we quoted out, we're half the cost of the 4-axis machining guy, and again, our lead time is 3 to 4 days. So you got to have a level of complexity that takes it out of like the Bridgeport type area. How am I looking on time? 5 minutes. All right. I'm going to try and just bang through a couple of these guys. This is another style gripper that we have in the back. Talking price again. Oh no, didn't want to do that. I can't actually see my, anyways, the price on these guys, if you ordered one set of these from us, so 2 gripper fingers, one set, about $340. If you ordered 5 sets of these gripper fingers, it's $120 a set, because you're filling up a layer of my machine. And when you fill up that layer, you're buying Z height. So if you just order 2 of those parts from me, you're buying the same amount of Z height no matter what. If you order 5 sets of those parts from me, all of a sudden you're using up way more of your Z height, but there's not enough to make the height go up. So now you're just paying for material. Material is the cheapest input to the MJF process. So, you know, we're like 80 cents per cubic inch fully loaded cost. To put that in perspective, my SLA machines, my legacy machines, is $4.25 per cubic inch fully loaded cost. So, you know, if you can take and either buy multiple of parts or take, you know, some of these gripper fingers, some of these gripper fingers, maybe some of the other parts that I showed you for like a specific application and batch them all together, the price just falls through the floor on all the parts. So if you have the ability to batch stuff together, you'll see massive cost savings just because you're utilizing more space on the machine. Kind of counterintuitive coming from traditional manufacturing of, you know, CNC or sheet metal or something like that. You know, yeah, more volume, the price per part will slowly tick down, but here the price just falls off a cliff. It's like straight down. I literally had a quote I did 2 days ago where I quoted quantity of 1, quantity of 5, and quantity of 10, and the price jump from quantity of 1 to quantity of 10 was $20. That's literally the difference, because it was a big part, but it used almost no material. So the price jump was almost insignificant. MJF springs, I'm way behind on time, but essentially you can print springs, okay? And you can come see me afterwards. I'll give you a lot more information on this, but essentially for momentary type applications where the spring is just being pressed down momentarily, or if it's like a detent where you're sliding over top of it and then the part pops back up behind it, works really good for that. Doesn't work in long-term compression. Long-term compression, the material picks up a memory and you don't get the same return force. So good for momentary applications, not as great for long-term hold type applications. Again, these parts are in back. Hand tools. This is one that we do for a company that makes tape, and they send a lot of, they do all the window companies. So Anderson Windows, Pella Windows, all down in Mexico. If you buy a double hung window from, you know, Home Depot, it is held together with tape, and that's it, just double-sided sticky tape. This tape company was spending a fortune in machining Delrin tape applicators, because there's all these different extrusion profiles that they're trying to work with. And so we were able to come up with a way to do these in MJF that was like half the cost, and we were also able to integrate a roller right into. That roller is printed, captured into the part. It's not removable. And so now, instead of just wetting the part or putting the tape on and then having to take a roller and wet the tape out by hand, one movement, and they've aligned and wetted out the tape in a single movement. So these are really good. And that's the end of my presentation. So, you know, thank you so much for your time, guys. And I think Dave's going to come back up here and we can answer some more questions. So how are we looking on how much time we have for Q&A? 6 minutes for Q&A. So any other questions? I can back up to slides we kind of breezed over. Yeah, sure. Come in back, grab my card, and I'd be happy to send you the presentation.
Absolutely, and my understanding is that this will all be available. We can view it anytime.
That's correct. Actually, on the website, we have an archive of all tech takeovers that occur. So this live presentation will be viewable on Automation Alley's website.
Yeah. One thing I wanted to mention: this very scary-looking. I hate. Tell the story behind that spider.
So industrial CT scanning. So we have our engineering business. We do a lot of reverse engineering, and so one of my vendors has an industrial CT. So just like if you went to the hospital to get a CT like chest scan or something like that, it scans in 3 dimensions. And the cool thing about industrial CT is it's scanning on a micron level, and it does all internals. So like, that spider was about the size of a penny, and the customer put it into a CT machine, scanned it, sent the file to me, and then I actually blew it up to about this big around. And the definition, put it this way, that thing, I'm way more scared of spiders now that I've printed one this big to see what they actually look like. I'm a bit more nervous about spiders than I used to be, because they're mean little guys. At least they look really mean. So yeah, the same with the bear skull. That was actually a black bear that was shot up in Alaska, and I got the skull and we CT scanned it. And the brain cavity, the sinus cavities, everything is inside there. We actually printed it split in two, so you can actually open it up and see all the brain cavities. So next time you're passing through Grand Rapids, stop by and I'll show you some cool stuff on the CT scanner with MJF.
Are there any additional questions at this time?
This thing cooks, man. Like MJF, I mean, that's the thing we like the most about it, is if we run a full build, it doesn't matter if it's one gigantic part like that flower pot singulator I was telling you about. We can fit 2 of those in a build, and it's a 16.5-inch build. And yeah, you're running at about an inch an hour. And then, but other applications, we have customers that we run 400 little wire harness management parts at a time for a furniture company, and we fill the same box but with 400 parts, and it runs at the same rate as the big parts that I can only get 2 of those in there. So MJF doesn't care. The analogy I like to use is, a lot of people are like, well, what's the difference between SLS and MJF? And I like to say, well, if I said, hey, you're going to paint a fence and you have a choice. You can paint a fence with a paint marker, or you can paint a fence with a spray gun. Which one do you think is going to go faster? Well, SLS is your paint marker, because you're sitting there coloring in every layer of the part. Whereas with MJF, it's a spray gun. It literally, for lack of a better term, sprays the layer on, heats it up, cures it, and then applies powder, and the process repeats. And what is it, guys, like 17 seconds a layer or something like that?
Sounds about right.
Lower? 12 seconds? I don't know. I can never remember. It's fast. It's really fast. Any other questions?
Well, I think we got our Q&A as we went along, which was a nice aspect. Are there any additional questions here before we close out?
So we've experimented with dry graphite, putting graphite in there to lubricate it. We haven't really done enough studying on that yet where I would have like a definitive answer for like it makes a huge difference. We tend to, like if you go in back, I've got some sample parts, and Novastar does too. Typically my rule of thumb is, if you have 2 parts and if you're printing them in an assembly, so where they're trapped with each other, we typically leave like a half a millimeter of space between trapped components. Sometimes we found that we can get within a 1/4 millimeter if it's like a corner that's within a 1/4 millimeter of a face. So sometimes we'll do really weird features inside of trapped components where we need to locate them as tight as we can, but we also need to make sure that we don't weld, because the part it'll weld itself together. You won't be able to get the powder back out again. So general rule of thumb, quarter millimeter if it's a corner to a face, or 0.25. Half millimeter if it's 2 faces running parallel to each other. And I guess one thing I will throw out there, I do lunch and learns all the time. Specifically, this presentation stretched out to an hour, and it's just designed for additive. I go through this presentation, and it's specifically for designers and engineers who want to design for additive manufacturing. It's literally going through and giving you the tips and tricks of how to design your parts to take advantage of this process. HP has powdered metal coming down the road, but that's a ways out yet.
Right. So the technology that's available to everybody right now is they're all polymers. Nylon 12, nylon 11, thermoplastic polyurethane, and polypropylene coming out not later this year. Hewlett-Packard has announced a technology that uses metal powder, actually uses MIM powder. And the way you access that technology is you basically will upload the file to one of 2 companies, Parmatech for pharmaceutical and medical applications, and GKN for industrial and automotive applications. You upload a file, then they send you a part. And there's information available on that on the HP website. Oh, by the way, we have Eric DuPaul, who is our contact from HP. And I think Eric has something to say about. Okay. Yeah. Yeah. Now it's using. Yeah. So you can access. Yeah, so you can access the technology through the early adopters. We have two early. They're basically like alpha tests, and it's stainless 316. I believe is the only material that's available right now. But that's it's a pretty impressive technology. I've seen some sample parts. We're doing some really neat things with some auto manufacturers. So if you do want to access that technology, again, you do it through uploading a file, and then they send you parts. Josiah, yeah.
Yeah, so traditionally SLS machines, the best powder rate you're going to get is 50-50. So 50% regrind or used powder, and then 50% virgin. And so you wind up throwing away a lot of powder because eventually you've got all this excess powder that's a mix, already mixed 50-50, and you can't keep mixing it in. So eventually you wind up throwing powder away. With MJF, it's 80-20, 80% regrind or used powder, 20% virgin. So we throw away way less powder than a traditional SLS machine, which helps us, again, keep our costs down and make our parts more cost effective, especially in high volume or high volume for additive manufacturing, low volume if you're compared to like maybe a injection molding type application, helps keep our costs way down. So detailing agent does build up in the powder. Excuse me. So yeah, that's why they're adding that 20% every time, is to dilute the old powder with new powder, so you still get a good spread when you go to recoat or lay a fresh powder layer or a fresh layer of powder down onto your build surface. But yeah, over time you do build up with detailing agent. So eventually that's what causes your powder to and it's not just, I shouldn't say it's just that, it's kind of it's a little hard to explain, but you've got used powder and eventually the ratio just doesn't work. Like you're always going to wind up, in our case, I know EMI, I think they have their build, they're running their machines in such a way where I think they're capturing a lot of powder inside of their parts where they're not sintering. They'll actually hollow their parts, leave powder trapped in the inside. So when I send you a part that's this big, it's actually just a 1/4 inch thick candy shell with a bunch of powder trapped inside of it. Still gives it strength. And for non robotic applications where you don't care about weight, it's just a way for me to keep your cost down. So a few rare companies like that have pretty much no material that they're throwing away. But like for us, some days I'm running big blocky parts where I can trap a bunch of powder inside of it. Other days I'm running tons of little itty bitty parts where there's no powder trapped inside of it. And eventually you just wind up with excess powder. And so yes, it's loaded with detailing agent, but I'm not throwing it out because it has too much detailing agent in it or anything. It's just I can't, I don't have enough need for all that excess powder. So it's not like I'm throwing it away because it's bad. It's just it builds up over time. But I have friends who run SLS machines, and I mean they're throwing away, ungodly amounts of powder for kind of the same reason, but they can't get as much mix out of theirs as I can out of mine. So they just wind up having to throw away a lot more powder, which again drives their costs up because they have to bury that cost into their per part production costs.
So the 80-20 ratio, that doesn't mean that you lose 20% of your powder. It means that every build is made with 80% reclaimed powder, 20% virgin powder. Unless you actually get too much of an accumulation, you don't have to throw the powder out.
Yeah.
And there's a couple reasons for that. One is the detail agent is basically evaporates away. It's not a residue in the remaining powder. And the HP has done some studies where they show the powder being used multiple times, and there is some slight oxidation, but it's very minimal. And that's largely a function of the technology. So we've used the acronym SLS, which stands for Selective Laser Sintering. Basically, there you have a laser that's tracing out the outline of the part and it's building up. And there's a couple of disadvantages to that technology, but one of them, as you want to print as fast as possible, you want to interact with the powder as least amount of time possible, so you have to use very high intensity laser, and you have to use more reactive powder. So the powder that's not being fused into parts tends to be more oxidized. With the jet fusion, it's interacting with the powder for a longer period of time, even though the overall printing process is much faster, so the powder does not have to be as reactive. Therefore, it doesn't oxidize as much, and it could be used in a higher ratio of reclaimed powder to new powder. So that 80-20 ratio doesn't mean you're losing 20% of your powder. It means every time you build unit with a fresh batch of another batch of powder to print more parts, it's using 80% reclaimed powder, 20% new. There's a processing station that does that mixing for you automatically, so you don't have to worry about measuring that out yourself. It all gets handled automatically. But unless you just get so much extra powder that you have to throw some away, that reclaimed powder is reusable. You don't lose it.
We typically keep our overflow tank about halfway full, and then as we build up excess powder, we're putting it into storage, and we keep a full box in storage of powder, which is 350 liters or kilograms or whatever. I can't remember.
300 liters, 130 kilograms.
Yeah, yep. And eventually when that box is full, we put it aside and we start filling another box. And when that box is full, we landfill the one that we had sitting there in storage. So, but that, I mean, like I said, we've been running the machine literally around the clock since September, and we are almost filling our second box of excess material. And I can tell you, I have a friend who runs SLS machines, and in the same time period, running about the same amount, I think they've thrown away like 5 or 6 of those boxes at this point. So it's just a massive reduction in the amount of powder that you're having to either warehouse or throw away.
Yeah. Go ahead.
Depends. I'll build you a completely solid part. That's not a problem. But it drives the cost up because I got to use I got to use fusing agent in that area, and that fusing agent is not inexpensive. And so a lot of times, like on nesting details, like and I don't have any good examples here because I didn't bring any big parts, but a lot of times on nesting details, it's a block like this, and we're just setting something into the nest. It's not a high load application. It's not seeing a bunch of forces. And so what we'll do is, to save costs on that nesting detail, we'll shell it, and we'll say, give us a 1/4-inch wall around the entire part and leave powder trapped inside. And that powder trapped inside helps to stabilize and keep the part, good and strong. But you're not paying for the detail or the fusing agent to fuse it solid. And so it actually produces a better quality part, because we found on big dense parts like that, we will get more tolerancing or tolerance issues. Whereas if we can keep a more thin uniform wall, we build a more tighter tolerance part. And we do that all the time, where we will literally shell out the inside of a part, and then we leave the powder trapped inside of it. Because honestly, for us to sit there and drain all that powder out and sit there with an air gun and try and get it completely cleaned out is way more time than just leaving it solid, and you get a better part and we get faster processing, so everybody kind of wins.
Yeah. So
I don't use HP software, so I'm going to defer to these
okay,
gentlemen.
so the HP software, well, let me back up and just give a little context. So say you're printing a 12-inch on a side cube. You could, if you wanted, have that completely be fused powder all the way through. It's going to be a lot heavier. You're going to be wasting a lot of fusing agents, and you're actually going to be wasting more powder to do that. So what you would typically do is, if you have a 12-inch on a side cube, you would put a hole in that you could drain out the powder. Or you could also just, as Paul referenced, fuse the outside wall to a certain thickness. Let me put it this way. The fused powder is more than twice as dense as the unfused powder. Now, the software that comes with the Hewlett-Packard system, loading, it works fine, but it's fairly rudimentary. There are much more sophisticated packages available, like Magix from a company called Materialize. And what they could do is you could just tell, I want a plug, and it'll basically design a hole and a plug, and it'll print those two. You'll dump the part out, screw in the plug, and away you go. So there certainly are multiple ways to address that. But the HP build, the software that loads the pack, loads the parts into the build, isn't as sophisticated as other parts that you pay for.
I use Magics.
Yeah, we do latticing. Next, the most current version, latticing built in.
Yeah, as a user, just plan on buying Magics. Like HP makes wonderful equipment, and I'm sure someday they're going to make wonderful software to go with it. Today is not that day. Yeah, so buy their machines and buy Magics.
And there's also NetFab from Autodesk, and I think there's something from there's another package.
There's a couple.
Yeah.
NetFab and Magics are your two big ones. And I will say, the sintering module for Magics for packing builds is also, it's expensive, but if you're running, especially a service bureau like us, it's worth the money because you can pack builds way faster with something like that. So.
Hey, if there are additional questions, we'd be glad to chat with you in the back of the room. We appreciate your time. We thank you for coming. We invite you to our open house. I do encourage you to, if you use LinkedIn at all, to connect with Paul DeWys, D-E-W-Y-S. He posts some really interesting and very educational things, and it's a good follow. Thank you for your time. Again, if you have more questions, we'll stick around as long as you want and answer any questions that you have.
Thank you, guys.
Thank you.